Okay, I think we're good.
All right, cool. So I am probably going to skip my introduction for the recording. I'm just going to go directly into the slides now. Um, all right, another try to share my screen. All right, can you see my screen?
Yeah, we're looking good.
Perfect. So I'm going into present mode. And let me know, and feel free to stop me, or like if you have any questions in the middle, or we can also take them in the end. So let's kick it off. So today I'm going to be doing a presentation on Intro to Ceph, which is an open source distributed storage system. It's not just a file system, it's a distributed storage system, and I'm going to talk about what exactly it is in further slides. And as far as my introduction goes, as I said earlier, I am a project technical lead for Rados, which is a component of Ceph. So today what I plan to cover in this Intro to Ceph talk is what is Ceph and why should we care about it, first of all. I will then transition into a little bit of the Ceph architecture. And as you can see, the first component there is Rados. That is the component that I lead. And then I'm also going to be touching on RGW, which is our object storage. It stands for Rados Gateway. RBD, which is the Rados block device. Cephfs, which is actually this Ceph file system. And then finally, we'll also touch upon some of the management plane of Ceph and what options do users have, and also delve into the community and ecosystem that we have around Ceph. So this is kind of what I plan to cover. Let's directly move into what is Ceph. So in general, Ceph is often defined as software-defined storage. It's also called unified storage, scalable distributed storage. In a lot of our Ceph t-shirts, you'll see it's called the future of storage. And a lot of our users also like to call it the Linux of storage. So these are kind of buzzwords you'll hear around storage. But essentially what Ceph is it's just an open source software. And when I say it's open source, it means that you can run it on any kind of commodity hardware. So note that it's just the software. So the hardware can be anything that you really want. So it can run on commodity hardwares. All it needs is IP networks to hook onto. And then the underlying devices can be of any kind, which is hard disks, SSDs, NVMEs, anything that you can think of. The interesting thing about Ceph is that in a single cluster, it can serve object, block, and file workloads. So what I described in my earlier slide, RGW, RBD, and Cephfs are the kind of workloads that you can actually essentially run in a single Ceph cluster. And that's something that is unique about Ceph, I would say. So let's move on. So Ceph is essentially free and open source. So when I say free, what does that mean? Anybody is free to use Ceph. As I said, it's open source. It's all our source code is on GitHub. So anybody can just start using Ceph. We have all our packages that we build that you can download and start running Ceph on your hardware even today. When we say that we give you the freedom to introspect, modify, and share, it also means that we want you to be part of the decision making or even contribute code to make the project better, the product better. So we welcome code from the community, and we have contributors from different fields, from academic fields, from industrial fields, and anything that you can actually think of. So that's where the freedom to modify and share also comes in. There is no vendor lock-in. As I said, Ceph is just the software. You can literally decide what kind of hardware you want to run it on. So your software stack remains the same. And if you prefer to run it on a different kind of hardware for whatever reason, you can essentially choose to do that. And finally, the freedom to innovate. Given that all our code is all open source and we have all our when we say open source, there is a word called upstream. So everything is upstream. So all our design discussions, all our code reviews happen in the open. So anybody is welcome to come and contribute code and add, innovative ideas into the Ceph code base. Moving on, Ceph is reliable. I do hear some chat, but I can't see it because I'm just sharing my screen. So let's hold off on any of those questions if they are for me up to the end. And if you want to ask questions, feel free to stop or say something that'll give me an idea that somebody has a question. So I'll keep going. So Ceph is reliable. So essentially, the idea is to build reliable storage servers out of unreliable components. So essentially, the software that we provide can be run on commodity hardware, which can be unreliable, but the software essentially makes sure that the storage capabilities and the redundancy and replication, etc., is taken care of by Ceph. So it also has no single point of failure. When I say replication, we have other ways of replicating data. We have just pure replication. We have erasure coding that we support. So data durability is taken care of by these mechanisms. And we also don't have any kind of interruption of service. Essentially, we support rolling upgrades. All our expansion is online, so your system can continue to serve the application that is running on it while you're expanding your system, and all that kind of stuff is supported. And finally, we favor consistency and correctness over performance. So anytime we are put in a hard spot where we have to choose, we do choose consistency and correctness over performance. We do give a lot of emphasis on performance, but as it said, so if some of you are aware of the CAP theorem, so in CAP you have like CP or AP. So essentially Ceph is CP, so it's consistency over availability when it comes to partitions. Ceph is scalable, so it's essentially elastic storage infrastructure. So you can grow and shrink your storage cluster based on your needs. And you can add and remove hardware while the system is online and under load, just what I described earlier. Based on your needs and your application's needs, you can scale up with bigger and faster hardware, or you can also scale out within a single cluster for capacity and performance. So it's entirely up to you what you want to optimize for. We also have something called federation, the concept of federation, where we federate multiple clusters across sites with asynchronous replication and disaster recovery capabilities. So this is essentially a Radar's gateway feature. I will be talking more about this if you're curious. So, all right, coming to this this diagram, and I think this is the diagram which is most commonly found when you actually go to Google for Ceph. This is one of the things that comes up first. This is a very simple picture that actually describes the architecture of Ceph. So on top, you can see there's object, block, file. So object is essentially Radar's gateway, which serves S3 and Swift object storage. Block is RBD, which is essentially a virtual block device. And as far as CephFS is concerned, it's essentially a distributed network file system. And what lies in between is the Radar's API layer, and what I actually take care of, and which serves all kinds of these applications, is Radar's, which you can see is sitting on the bottom. So Radar's is this layer which essentially interacts with the hardware. And all these kind of applications that are running on top are actually talking to Radar's to serve any kind of I/O. So Radar's is this reliable, elastic, distributed storage layer, which provides replication and erasure coding. So let's talk more about Radar's now. I would like to like stop and ask: are there any questions, or should I keep going?
There are some comments on the chat.
Okay, I'll have to probably get out of screen sharing.
Oh, I can read them.
It's just commentary.
Yeah.
Okay, turns out that stopping share screen share is actually crashing my browser. So sorry about that. But let's go to the questions. I was going to ask, what does Ceph stand for? Ceph it's not really an acronym. It's just a term which was chosen because of, I mean, if you notice, like Ceph has this association with octopus. So, I mean, that is where even our t-shirts and everything have octopus. And even our releases are named based on. So yeah, I think the cephalopod is where the Ceph word comes from. But all our releases are in alphabetical order, and we try to choose words which are related to cephalopods or like octopus or like sea creatures in general. So that's kind of where Ceph comes from. But I guess that's the only question. Are there any more questions?
Sounds good. Thank you.
Cool. Yeah, no problem. But just in favor of not crashing my browser again, let me just quickly try to share my screen. All right, can you guys see my screen?
Looks good.
All right. So we were here. So Ceph is actually not an acronym, but RADOS is. So it stands for Reliable, Autonomic, Distributed Object Storage. So this is the common layer that sits underneath and is responsible for underpinning object, block, and file services. Now, it provides this reliable, highly available, and scalable storage system that you can actually run any kind of application of your choice on top of. It takes care of all the replication and the erasure coding, data placement, scrubbing, data integrity, rebalancing, repair, etc. So essentially, the application doesn't need to take care of anything. So as long as you're using the API to talk to RADOS, RADOS will take care of all these kind of things. And as I mentioned earlier, we provide strong consistency. So we favor CP over AP in the CAP theorem. And this whole, so this common layer sitting underneath in the architecture, it kind of simplifies the design and implementation of the higher levels. All they need to do is to be able to use the API, the LibRados API, to be able to communicate with the RADOS layer. All right, so let's now talk about some of the, so as I said, Ceph is software, RADOS is also software, so there are some components that come with it. So in RADOS, there are particularly these three components, and I think it's important that we look at these pictures because these pictures or these symbols are going to show up in future slides as well. So essentially, you have something called CephMon, which is the monitor. This is essentially the central authority for authentication, data placement, policy, etc. Coordination is one of the major things that monitors do, and it also takes care of critical cluster state. And we have an implementation of Paxos, which we use for such coordination. In usual scenarios, you have 3 to 7 per cluster. I must say that it's 3 to 7 and not 3, 4 because we need odd number of monitors break ties. So moving on, the next component is called a manager. So unlike the monitor, you don't have 3 or 7 of them. You generally have one active manager and 1 or 2 standby. The idea is that they don't really have any state. But in case there is something wrong with the active manager, it just the standby just becomes the active. So you fail over. What these managers do is essentially they aggregate real-time metrics like throughput, disk usage, etc., from different daemons in the cluster, and they kind of aggregate it for higher level services. When I say high level services, the manager also has these pluggable management functions called modules. So there are implementations written in Python in the manager, which can use all the metrics that are collected from the cluster and do things like, we have one of the most common ones is the dashboard. So dashboard uses all these kind of metrics and all the cluster state and displays it to the end user. There are also optimizations that we run in terms of manager modules on the cluster. So the manager is essentially responsible for these kind of pluggable management functions. And finally, object storage daemon, which is the OSD, which is the daemon that is responsible for actually writing data or storing data on hard disks or SSDs or any kind of hardware. They essentially serve client I/O and are not just like dumb daemons, I would say. They are active in cooperatively peering. They talk to each other. They exchange heartbeat messages. They take care of replication traffic, rebalancing, and you can have tens to thousands of OSDs in your cluster based on what scale your cluster is and what kind of application you're trying to run. I think the largest we've heard is we've had like more than 10,000 OSDs in a cluster that was running Ceph. So moving on, now let's go into the architecture of Ceph, and I would like to start by talking about the legacy client server architecture, which is not what Ceph uses, but the problems that we saw in it and we decided not to use it is like, essentially when you have an application and a server, when you have just one server, this kind of model works fine. But when you have multiple servers and when you have a distributed system, this kind of architecture does not scale. So there have been tricks like virtual IPs, failover pairs, gateway nodes, etc., that have been used. But what we have in Ceph is something even better. So what we like to call our architecture is client cluster architecture. So the idea is that you have an application and you have some sort of smartness in the application that does smart request routing, flexible network addressing, and even simple application API. Like the application API is simple, so the application knows which exact storage daemon to go talk to based on some information that is stored in the network addressing table that we have. So as you can see in the bottom, you can recall some of those symbols that we saw, the managers, monitors, and OSD. So that is essentially what defines a Raiders cluster. So how is data placement actually done? That's a big question because we have an application and you have a data object. So in Raiders or like even in Ceph, the granularity of data being written is in terms of object. So when you have a data object, how do you know where to write that object? So one option could be that you could have like a metadata server which has all the information of where this data object is stored. So an application would first talk to the metadata server, find out where to look up this object, and then go directly talk to the object. Now, the problem here is that lookup step is slow and it is hard to scale when you reach trillions of objects. So what we have instead is what we call calculated placement. So the idea here is that So if you see on the top here, the monitors essentially hand out key piece of information to the application that lets them figure out where exactly the data object lives. So in this case, you can see that the monitor hands out like a cluster map or a layout of the number of OSDs that are there, or what the cluster looks like essentially, and the application can use some intelligence to figure out where exactly that data lives and go directly talk to the data instead of going to a metadata server. So this calculator, I'll talk about how this calculation is done in the next slides, but the idea is to use some sort of smartness here and directly talk to the storage daemons and eliminate the middleman or the metadata server from the picture. Now the next question is what happens when the map that I said earlier is shared with the application and the topology of the cluster changes. In that case, there's periodic exchange of these maps that happen from the monitors to the application. So once there is a node failure or the topology has changed because you've added nodes or removed nodes, etc., these new maps get propagated to the application, and then this calculation step happens again, and we deterministically figure out where to read and write from which OSD to read and write your data from. Now, moving on, I talked about what objects are, but now let's see what they actually have. So every Radar's data object has a name. This name could be tens of characters. As you can see, there's an example here. We also have attributes. Now, these attributes may or may not be used based on the application that you're running, but you could have something like a version. You can think of something like a version, which is an attribute that you can store in an object. Now, when it comes to data, there are two kinds of data. So there is byte data, which could be from 0 to hundreds of megabytes. And then there is something called OMAP, which is key value data. So these key value data, as you can imagine, like they are key value pairs that you can store in each Radar's object. And you can do that for like tens or 10,000s of items. And in a lot of scenarios, you'd either have byte data or you'd have OMAP data. In very rare scenarios, would you have both? But each Radar's object is capable of storing all of this. So the picture on the right tells you like all these objects are living in something called pools. So we have this construct of pools. So all these objects, any Radar's object is part of a Radar's pool. So that is why we say it lives in named pools. Now let's, the next slide will actually tell us how this placement is happening, or like an end-to-end picture of where the application has a file that it needs to store in Rados and the OSDs, and what are the steps involved in doing that. So you can imagine that on the left, you can see all kinds of applications, like you have a video file, you have a picture, you could have like just a regular file. In this example, we are choosing this foo.mpeg file. So what objects mean is that this huge file is divided into multiple objects, and these, is the naming here suggests, are sequential. So you're just breaking one big file down into multiple objects. And Rados has a size limitation, or like we have a default object size that we use. So you can imagine something like 4 megs that you're breaking this big file into. Now, as I mentioned earlier, like all these objects belong to a pool. So you can imagine like a pool has bazillions of objects where it's actually storing a petabytes of data. Now, in order to easily reference what objects are, we have another construct which is called placement groups. So each pool essentially gets divided into multiple pieces. And in this case, you can see we have 4096 placement groups. But the idea is to break each pool down so that all these objects that are present here will be part of one of those placement groups. So the way we do this, the divide is using this function here. So we do a hash of the object name. Like I mentioned earlier, each object has an object name. We do the hash, and then we do a modular to decide which exact placement group an object is going to be part of. So essentially, you're distributing all these bulk of objects into different placement groups. Now, these placement groups in turn have OSDs that they get mapped into. So each, based on what kind of replication strategy you want to use, like in this example, you can imagine that this 1.0 has a replication strategy that we want 3 copies of this data. So there'll be a bunch of OSDs, and there'll be 3 OSDs that will be picked to store this 1.0 data, which is there in this placement group. And similarly, you can extrapolate the logic to the rest of the PGs that are there in this cluster. So the idea is this big file here gets broken down into objects. Objects are part of a pool. Now pools are divided into placement groups, which in turn live in different OSDs, and there are n copies of each PG based on like what n you choose. All right, now some may ask why do we even have this construct of placement group, and why not just replicate like you have disk A, just replicate disk A in 3 different disks. It's almost the concept of mirroring, right? So the problem here is that each device that you have here should be of the same size. Otherwise, you are going to be able to write only data worth of the smallest device possible, which is there in your group. So that way you are basically wasting storage. The other thing is that when you need, let us say there is a failure and you need to replicate to a new disk, what you need is an extra spare disk that you will copy your data into, and then you will actually be bound to the throughput at that spare disk that you use for recovery purposes. Now, if you use the concept of PGs that we talked about earlier, replication in PGs is not done per disk. So essentially what can happen is, like here you have these colors. So this cream colored you can imagine this is one PG is living in 3 separate random disks. So if, let us say, there is a failure of one node, this particular node here has PGs of cream color and PGs of blue color. So if there is a failure of one node, you'd have to find a new place for this cream colored PG to go to, and another for this blue colored PG to go to. But this time you can choose randomly new any other disks. You don't have to replicate the entire disk in this case. So it's easier, and it's and since the placement is random, you can the probability of again picking the same new host for that PG is very low. So you'll probably be picking 2 separate hosts. So the recovery throughput is also not going to be bounded. So essentially you can do 2 recoveries versus 1 recovery at a time in the first case. And finally, we can go the extreme route and say that we don't even need the concept of PGs, and we can replicate objects. Like we can choose any object to place in any disk that is there in the cluster. Ideally, one can do that, but the accounting and even the probability of failure, or like even grouping failure domains, becomes a real challenge in this scenario. So what we've decided to do, this is another explanation of why replicating by disk is not a great idea, because you need an empty spare to recover that disk, and you again bottle what I already touched upon. And in this case you don't need a spare disk. In both these cases you don't need spare disks, but the final case here, what would happen is that if there is a disk failure, given that any object can literally reside in any disk, you'd have a lot more recovery participants in terms of OSDs that are there. So what we have decided to go with, in Ceph with, is this replicate through PG concept. Now the next part is about what are the downsides, I would say. So like replicate, if you replicate by disk, in cases of triple failures, there is very little chance of data loss. But in terms of when you have replication by object, there are very high chances that 3 of your different objects that are part of different PGs are in the same host. So you could essentially lose all the copies. But in case when we have replication by PG, the probability, like I described earlier, that when you lose one host here, the probability of losing all 3 copies is very low. So in this case, when you lose, let us say this disk, when you had the replication by object, all the 3 copies of your object can potentially be in one disk. So it's possible to have complete data loss. So I guess this replication by PGs is a mix of both worlds, and not too extreme in both cases. It kind of works for most scenarios. So about keeping data safe, I guess in academic literature, this is called declustered replica placement. So the more number of clusters you have, the faster your recovery is going to be, and more even the data distribution is going to be. And in fewer clusters, there's lower risk of concurrent failures affecting all replicas, like we saw earlier in the first case. But I guess placement groups is kind of the middle path here. So you don't need any spare devices. You can adjust the balance between durability in terms of concurrent failures, and you also are not spending too much time and making your recovery process efficient. So in terms of avoiding concurrent failures, there are concepts in Ceph that allow you to do that. So you can do things like place your data smartly so that even if you have a failure, the probability of losing or complete data loss is very low, and the probability of that loss affecting the cluster's availability is also very low. So like we have these separate replicas across failure domains. So what you can do, things like you can say that if you have 3 replicas, you can say that I want all my 3 replicas in different racks. So in case when there is a host that fails in a particular rack, then you're guaranteed that only 1 copy of your data will be affected, and not more than that. And there are other rules like that you can come up with based on your requirements. There's also a hierarchy of storage that can be created just by using the same techniques, and expressing placement policy in terms of hierarchy, of this logical hierarchy. You can do that and ensure that your physical locality kind of maps to this placement logical policy that you create based on where your data center is or where your disks and racks reside. So there is, I will talk about Crush in Ceph, which essentially helps you do that. But there are multiple ways in which you can make sure that your data is safe in the Ceph cluster. So this is what I wanted to get to. So placing PGs with Crush. So Crush is an algorithm, and there is a paper. So there's a paper on Rados, there's a paper on Ceph, and there's a paper on Crush. And anybody who's interested, I would really recommend that they read this paper. But the general idea is the placement that we were talking about earlier is done by Crush. So Crush is nothing but a pseudo-random placement algorithm. It's repeatable, deterministic, and it calculates the same thing every time. It's very similar to consistent hashing. So in this picture on the right that we saw earlier, this algorithm takes inputs like cluster topology, what kind of OSD hierarchy you have, what is the replication factor, what is the PG ID, and what it would spit out is like a list an ordered list of OSDs that you should be placing your data in according to crush. So essentially, like when you give in the picture on the right, it came up with this first one, third one, and the fourth one based on whatever parameters we provided. So that's the general concept that crush uses. And it also and this it is so I've been describing a very simple replication a policy, but it also supports erasure coding. So like you can do things where you can set up an erasure coded pool and make sure that your failure domain is such that you can lose n number of copies without losing data. So yeah, I think before we move to the next one, I think there are a couple of other things I would like to touch upon. So one limitation that we saw earlier about when we talked about disk replication at the disk level was that you needed to have all the devices of the same size. But with when we have placement groups and when we have crush, you can do things like, let us say you have a mix of SSDs and hard disks, and some of your SSDs are smaller and hard disks are larger. So you can vary the device sizes and tell crush that you want to place lesser data or fewer PGs on your SSDs versus what you want to place on hard disks. So it's not like an umbrella number or like number of PGs that we get bottlenecked by. So we can assign weights to OSDs based on the device type that they are on, they're hosted on. All right, so let's now talk about, so before I move to replication rate, I didn't hear any questions. Are there any questions so far? I'm not hearing anything, so I will keep going. All right, so the next part here is about replication and erasure coding and how do we actually do that in Rados. So each Rados pool has a property which decides whether the pool is going to use replication or erasure coding. And this is just for durability purposes. So in replication, what we have is identical copies of each PG. So essentially in this picture, you have two objects, data and my object, and the same objects are replicated three ways. So there are three separate OSDs that have the same copy of your data. Versus in erasure coding, if you see, the concept of erasure coding allows you to shard the data into multiple pieces, and then you have these coding chunks. So here you essentially have, like you can see, this is a 4+2 erasure coding scheme. So you have shard 0 to shard 5, where 0 to 3 is essentially storing the data bits, and you have the rest of the two other parity bits. The difference in erasure coding and replication, one major thing would be the overhead. In replication, the overhead is 3x, which is essentially 200%, because you're essentially storing the same data in 3 places. But with erasure coding, the overhead is clearly lower because you only have actual data in 4 places and you have just 2 coding chunks. So if you lose a couple of copies out of this, you should be able to, I should say not copies, I should say shards. If you lose a couple of shards, you should be able to recover your data just fine. So the storage overhead is lower in erasure coding, but when it comes to recovery time or rebuild time, replication is much faster, because essentially what you're doing when you lose one copy of your replicated pool, you are just copying from one of the available copies. But erasure coding doesn't work like that. You need to be reading multiple copies to rebuild the data and generate that new shard again. So there is extra complexity and recovery time that comes with erasure coding. But if you just want to optimize for space, erasure coding is something that you can use. So I guess and Ceph supports both we do have recommendations as to when you should be using replication and when you should be using erasure coding, but in terms of supporting, we support both. All right, moving on. So specialized pools. So in Ceph, you can do things like you can just use a mix of pools in the same Rados cluster. So you can imagine you have a 3x replication SSD pool. You have another pool which is an EC pool, an erasure coded pool which is on hard disks, and you have another one which is just hard disk but using replication. It's totally user choice, I would say, as to what you want to use. Pools essentially also share devices. This is until and unless you tell Crush not to. So if you just create a Rados cluster and create 3 different pools, you would be sharing all the devices. But there are ways in which, if you do not want to share pools and you want, let us say you want your SSD pool to be restricted to only a few set of OSDs, you should be able to do that as well. It is elastic in the sense that you can deploy new hardware and the existing Rados cluster can consume the new devices that you've added. Existing pools can also use that. The only challenge is that with erasure coding, the decision of how large your pool is or what your K and M parameters are need to be taken at pool creation time. But for replication, it's as simple as you can increase your replication factor by just changing a configurable in the pool. And so you can go from 3x replication to 5x replication based on your need. But in erasure coding, you cannot do that. So that's one difference. But in general, adding and removing devices, etc., should work the same. So in a way, Rados is actually virtualizing storage. So you have multiple applications that are running on top. They may have different storage requirements. They may have different performance requirements, but they can actually essentially share the same Rados cluster by means of creating these separate pools that are going to consume the same devices underneath, which are controlled by Rados. All right, so I think this going back to the same picture. So now we have a good understanding of what this Rados layer provides. And now I think we will go a little bit into the higher level stuff or the platforms that are supported by Rados. But before that, I did hear some things. Are there any questions in the chat? Okay, if not, I'm just going to keep going with RGW. So RGW, as I mentioned earlier, it stands for Rados Gateway. It provides object storage for Ceph. It is essentially S3 and Swift compatible object storage tunneled over HTTPS, and it's REST-based API. People often combine with the load balancer, but you can imagine RGW providing storage for the public internet or even private clouds. So in S3, in RGW, what you have is this concept of users, buckets, and objects. Now, these are S3 constructs as well. But these objects are different from Rados objects that we talked about earlier. So these essentially have data and permission models, which are based on S3 and Swift APIs. And they also have ACL-based permissions enforced by RGW. So these permissions can actually be set in the RGW layer, and there's nothing much happening at the Rados layer. So essentially, these RGW objects, which are much larger, I would say, compared to Rados objects, which have a definitive size. So these large RGW objects are broken down into Rados objects, which are then striped across the Rados cluster. So that's essentially what the picture on the right tries to say, that you have the RGW, which is talking this S3 compatible language, and then you have the Rados cluster, which is essentially storing all the RGW objects by strapping it across the Rados cluster. All right, so RGW stores its data in Rados, and how does it do that? So this picture kind of tries to explain what the workflow is. So when you do an S3 level put, what happens is, and you can imagine RGW like Amazon's S3 servers, an equivalent of that. So essentially any S3 put or post that happens comes to the RGW layer by means of this Rados API layer. We have first this concept of bucket, a user plus bucket info pool. So this pool is a Rados pool, but this pool is the first thing that gets used when an S3 request comes. So the idea is to check whether a user with that name exists, whether a bucket exists or not. So essentially checking for the validity of the request that has come in. So at this point, we are just contacting this info pool. This is just the information pool. So once we get an acknowledgement from this pool that everything looks good, RGW then talks to this next pool, which is the bucket index pool. So this bucket index pool is required because we have this index, which is essentially a sorted lexicographic. It is required for sorted lexicographic enumeration of buckets. And that's something that S3 also uses. So essentially, any request that comes in makes an update to this index pool before it actually goes and writes to the data objects. So step 2 is done here. And after we have updated the index pool, we go ahead, RGW essentially talks to this data pool, which finally does the IO to disk. And then after the IO completes, there is a step of updating the index object, letting the index object know that this IO has completed, and that's where kind of the request finishes, and the client gets an acknowledgement. So as this mapping back to Rados, I think the three common things here are 3 different pools in RGW being used for different purposes to fulfill an S3 kind of request. So moving on, so RGW also has RGW zones. So what a zone has is it could have multiple RGWs, as you can see in the picture, and it could have multiple data pools. It could be a mix of replication and erasure coding as described in this picture, but you again have this info pool and the bucket index pool, and this in entirety, all of these together will construct what we call is an RGW zone. In itself, it doesn't mean much, but if we move on to constructs like RGW federation and your application, these zones are what play a major role in providing the functionality. So essentially, in the picture here, what you see is that there are multiple zones, zone A1 and zone B1. Each of them have their bucket info and index pool and data pool. And then this arrow here. So essentially what this arrow says is that the info, the bucket info of the information that is stored in RGW is present in both the zones. So essentially there could be a request that comes in to this RGW in zone A1, and it is quite possible that the data that it needs to serve is not present in A1. So this bucket info will now redirect the request that has come in by just looking at the information and checking whether that information is present within zone A or not. If it's not present, what it does, it redirects this request to zone B1. So it's essentially the bucket info pool that has information that it is using to figure out whether the request can be fulfilled by the local zone or it needs to contact a different zone. So I guess the idea is that it has a global view of users and buckets. So it would your request may land in any of these zones, but it will be served by the correct zone without you having to do anything. It's the RGWs that are redirecting the requests. Now, expanding on this, we also have this construct of zone group. So what is different about zone groups, and you can imagine these zones and zone groups being in different parts of the world, different continents, or just different geographically separated locations. And these zone groups, what they essentially have different is that as you can see these arrows here, these indicate that the data that is present in these index pools and the data pools is also replicated. Now, there is one-way replication and there is two-way replication. So essentially, it is possible that when your client writes to zone C2 and there is a other client reading from zone C1, there is asynchronous replication that keeps going on, even if there is an update that was made to the same bucket that is present in C2 and has not yet been updated in C1. So we make sure that the bucket gets updated before we serve the request. So there is a concept of asynchronous replication, but here the only thing different is that the data is also replicated between zone groups. Okay, so among other things, so as I mentioned, this is essentially S3 API compatible, and we try very hard to make sure that it works fine in terms of RGW features and we don't break compatibility. So we have a full-fledged suite of tests that are compatible that we call Ceph S3 tests. And it's a functional test suite. And as far as I know, it's not just used by Ceph, it's used by other software projects that are also building similar products. And this is something that we maintain and run regularly to make sure that all the RGW features that land are compatible with the S3 API. RGW also supports STS, Security Token Service. It's basically a framework for interoperating with other authentication and authorization systems like Kerberos, etc. There's also encryption and compression. So when it comes to compression, so you could do things like compress the data at the RGW layer before even writing it to Rados. So RGW essentially supports that. And there are other things like course and static website hosting. There's another, what is interesting is the metadata search with Elasticsearch. So we also support the metadata that we store in these metadata pools, we support search in terms of Elasticsearch. And we also have a PubSub implementation. So this is fairly recent, but has been merged a couple of releases ago, I believe. So here the idea is that it's event-driven. So PubSub just means that if there is a bucket that you write to, it will trigger a Lambda somewhere else in terms of like, it's an event that will be driven based on the action that has been done on a particular bucket in the Ceph cluster. Now this helps with integration with things like Knative serverless and Kafka. And then there are other things like, as you can see, there are a lot of features that we provide. We have multiple storage classes, so you can decide what kind of Rados pools you want your RGW data to live in based on performance requirements, SLAs, etc. And the idea is that you can also apply different policies on these data objects that are getting stored in Rados. So essentially, you could have a separate pool where you have a different policy that is applied by RGW, which is actually getting stored in a different Rados pool. Now, there are also lifecycle management things. So essentially, you could set policies where you want something like automatically move my objects between storage tiers after a particular amount of time. and that is all time based. So you can move between tiers or even expire things from a particular tier based on time. And finally, you can do something like archive zones. Archive zones are essentially creating a full history where you're preserving all the storage history in the Ceph storage cluster, no matter what kind of policies are there. So these are kind of mostly used by archival use cases, I would say. But RGW lets you do that. Okay, I think that's where we are going to be wrapping up RGW. Are there any questions on RGW, or can we move on?
No questions here.
Okay, so let's move on to RBD, which stands for Rados Block Storage. So RBD is essentially a virtual block device which lets you store disk images in Rados. So you can stripe data across RBD data across many objects in an RBD pool. The idea is to be able to decouple your host, your hypervisor, almost analogous to what AWS's EBS is. But here you have two kinds of client implementations. So one which is virtualization based, and one which is essentially a Linux host. So in terms of supporting both kinds of architectures, so we have librd that we use for a virtualization stack, and we have krbd, which is kernel RBD, that we use for the Linux host side of things. But finally, what is serving the RBD pool beneath is the Rados cluster. So RBD has integration with libvirt. OpenStack is one of the biggest users of RBD, I have to say, and things like Kubernetes, Proxmox, CloudStack, other things which are probably not listed here as well. So these are a couple of main use cases of RBD. And now let's move on to what kind of things you can do with RBD. So one of the basic things you can think of with RBD is snapshots. So snapshots are just read-only associated with individual RBD images, and they are point in time consistent. So if you take a snapshot, you're sure to have a point in time consistent image or a snapshot of that particular image. Now, there's also things like clones, which are the next level. So essentially, the difference here is that snapshots are read-only, while clones are writable overlay over an existing snapshot. So one of the use cases that I can think of is like you could have a base OS, which is like a snapshot of like a fresh install that you've done. And then you could have clones like here in this picture, VMA, VMB, VMC, that are clones based out of this base OS, which you can further snapshot if you need to, but then you can start using them or like efficiently in O1 time creation. You can start consuming these clones which are created out of these snapshots. Now with clones, you can do things like resizing them, renaming them, etc. But the general difference is what I just described earlier. Now moving on to the data layout. So essentially every RBD image maps to objects, and these objects have the header part of it and the data part of it. Now the header part of it has things like name, size, striping parameter, basic metadata in the sense whether it has snapshot or not, that kind of information, and other options and locking ownership information. And the data you can imagine is essentially chunks of block device content. So it's like the RBD image is getting striped onto 4 MB Rados objects, which is again the configurable I mentioned. But the interesting thing here is objects are only created if and when data is written. So if you just create an RBD image of a particular size, only the header objects get created. These data objects don't get created until and unless you actually start writing to the image, so which is good. And again, like all other applications we've talked about, they support replicated and erasure coded based on whatever your choice is. Now, RBD also has a journaling mode. So the concept of a journaling mode is that all the writes that are coming through are first written to a journal, and these are most recent writes, including any metadata changes. And the journal also gets trimmed based on age, but the general idea is anything that comes in first gets written to the journal and then gets flushed to the data objects. Now, in general, this does on its own doesn't make too much sense, but it starts making sense when we talk about RBD mirroring. So the concept of RBD mirroring is extrapolating this earlier picture that we had, where you had librd talking to a journal pool and a data pool. Here we have something called an RBD mirror daemon. So it's a separate daemon that is sitting here and trying to talk to these two clusters. So the idea is that this journal pool is essentially talking to this RBD mirror, which asynchronously replicates the entire information that is there in cluster A to cluster B, and again creates a point-in-time crash consistent copy of the image in a remote cluster. So all this happens just by mirroring the journal. So it's reading the journal that is present in cluster A and writing out to cluster B asynchronously. So this is how you are asynchronously replicating across clusters, which could be, again, in different parts of the world. But the idea is to be able to mirror live data and snapshots and maintain a copy based on whatever requirements the application has. Now, each of these RBD mirror daemons, based on how many images are there in the Ceph cluster, you can scale them out. You can have multiple RBD mirror daemons, but it depends on kind of the scale that we are running at. Okay, so talking about other RBD features, RBD top, it's a nice feature, like it's essentially a command that lets you know what the real-time view of the IO activity in different RBD images is, which comes in handy a lot of times. You can also enforce things like quotas on different images. So these can be done at provisioning time to make sure that any client is not exceeding its quota. And also, in terms of isolation, there is something called namespace isolation. So if you want to restrict the permissions that clients have on, or like you only want some clients to operate on certain RBD images and not all RBD images, though you have other RBD images in the same Rados cluster, you can do that just by means of namespace isolation. And you can also do things like import, export, also do incremental diff between the snapshots you've taken over different periods of time. And you also have this RBD trash concept, which lets you keep deleted images over a period of time before purging. So it's essentially holding onto it for, again, maybe for archival purposes or anything else that you have a use case for. There are different ways in which you can consume RBD. The Linux kernel client, there's an NBD client, depending on whichever use case works for you. There's also an iSCSI gateway, and also a librd implementation that can be dynamically linked based on your application needs. So these are kind of the implementations users can choose from. All right, so we are now going to CephFS, which is the final platform / application that Ceph supports. And this is essentially the file storage. So sometimes Ceph sometimes gets confused as a file storage system, but it's not just file. We describe the other things. This is the file aspect of Ceph. I would say. So essentially, CephFS is a distributed network file system. So there are files, directories, rename, hard links that you can create in a CephFS cluster. And you have the ability to do concurrent shared access from many clients. So multiple clients can write to the same files in the Rados cluster. CephFS does provide strong consistency and coherent caching by means of locking and other kinds of mechanisms in the code base. But the idea is that what you see from one node in a particular file or a directory in CephFS, that's the same thing that you see from a different client's perspective. So that's how it's strongly consistent. There is another daemon that I'm going to introduce, which is the MDS, which is the metadata server, which CephFS is the only user of. But what it allows you to essentially do is scale metadata and data independently. So in this picture, you can see that the data here is getting directly written to the Rados cluster. But there is this metadata where this new daemon type shows up. This new picture here is essentially the metadata daemon that the CephFS client needs to talk to before operating on the data part of it. Now, all operations don't need you to talk to the metadata server. So essentially, the CephFS host can directly talk to Rados objects just while doing reads and writes. But when it comes to creating directories or listing directories, etc., the metadata server is what it needs to talk to. So yeah, this is what I was exactly talking about, the metadata server. It's actually a managed file system namespace. It helps coordinate file access between clients. It does so by the strong consistency that it provides is by means of locks and leases and other kinds of complex mechanisms that are there in CephFS. But the idea is that, again, this is like the manager daemon that I talked about earlier. Like these core components, the MDS, you'd have one active and multiple 1 to 10 of active plus some standbys. So essentially, when the main MDS fails for whatever reason, the standbys can take its place. But depends on like how large your cluster is. You can choose. You could even have one main and one standby, or you could have multiple standbys, depending on your use case. All right, so now this is a more detailed picture of how metadata is stored in Rados. So as you can see, this is a little different from RBD, I would say. So clearly you can see two pools here. There's a metadata pool and there's a data pool. So all the data that CephFS writes is stored in the data pool, and for all metadata purposes, there's a different pool. Now you can do smart things like if you want to make your metadata access faster, you can store the metadata pool on a faster device like an SSD, and you can store your data pool in a hard disk. But Ceph doesn't force you to do that. That's just optimization that you can do. But in general, the idea is that all the metadata goes into this metadata server, and it gets stored in terms of directories and metadata journal in this metadata pool. And the data part of it, again, is something that the client directly talks to the OSTs and reads and writes from it. So even in CephFS, you can do snapshots. The thing that is different in CephFS compared to any other similar product is that snapshots can be done on any directory. And it applies to nested files and directories. And this the granularity is at volume and subvolume levels. So essentially, you can snapshot any directory that is hosted in your CephFS cluster. These snapshots are again point in time consistent from the perspective of POSIX API at client level. Now, as you can see on the right, there are simple things that you can do to even create snapshots. It is as simple as that you do a makedir in your local.snap directory, and it creates a snapshot. And when you want to delete it, it is as simple as doing an rmdir of that snapshot. So snapshot management per se is pretty easy and efficient in CephFS. And similar, the concept is again similar here, that snapshots only consume space when any kind of changes are made to it. So if you just create a snapshot, it is not going to consume any space in the cluster. All right, so moving on to other CephFS features. So you can have multiple CephFS file systems per cluster. You could, each of those CephFS clusters could have different MDSs to cater to the underlying storage, but it lets you create multiple file systems within sharing the same Rados cluster. You have things like XAdders and file locking that CephFS provides. You can again have quotas similar to what I described for RBD. And you can do things like access restrictions on a subdirectory level. You can also create tiered storage, similar just by using the Rados pool capability of segregating your storage based on the application needs. You can create different storage tiers and adjust your striping strategy based on the cluster setup. And there's also things like lazy IO that you can do. So these are, I think, for mostly advanced users, where you optionally relax this CephFS consistency requirements on a per file basis for mostly for HPC applications. And in terms of how you can use CephFS, there's a Linux kernel client for it. We also have a Ceph Fuse implementation, NFS and CIFS implementation, and a basic libCephFS for those who want to run their own application using CephFS. So these are kind of ways multiple ways in which you can consume CephFS. And I think that kind of completes the whole storage platform story. So we have now touched upon all the building blocks here. Are there any questions at this point, or should I keep going?
I guess you can keep going.
Sounds good. Okay, so now we've talked about the applications and Rados and things like that. Now the question comes like, how do you manage a Ceph cluster? First thing that I want to talk about here is an integrated dashboard. So the dashboard works as a manager module. So you can just enable it after setting up or installing a Ceph cluster. And you can give it a port on which you want to host this dashboard. And essentially, it helps you do multiple things. One is monitor the health of your Ceph cluster, the overall IO capacity, utilization, the status of your separate, all kinds of daemons that are there in your cluster, the status of your hosts, everything. It gives you a snapshot of how the cluster is doing in general in terms of monitoring. Then comes metrics. So there is multiple metrics that the manager captures, like I described earlier. Now these metrics are used and displayed in multiple ways. So we have a Prometheus manager module that captures all these interesting metrics and aggregates them in a different level. And we have Grafana dashboards in this Ceph dashboard that consumes all those metrics and creates these user consumable graphs that make more sense to users. So dashboard is one way of like looking at the stats of your cluster or how your cluster is doing over time, just in terms of Grafana dashboards. The final thing is in terms of management, so you can do things like change your configuration, you can provision new OSDs, you can do all kinds of day-to tasks that you can think of just by means of the dashboard, and you don't need to use the CLI if you don't really want to. Having said that, we have a CLI which a lot of people use and like to use, which is always an option, but the dashboard is kind of easy and more intuitive and helps you do a lot of things very easily. Among other management features, so Ceph has a whole bunch of health monitoring, which is visible on the dashboard and also using CLI tools. The idea is to be able to raise warnings and alerts and errors in terms of states. So each warning that we raise or each error condition that we raise has a particular meaning. And so each alert has an ID. And each ID is documented, and if you run into a particular situation where your Ceph cluster is coming up with a particular alert, there are ways of going up and looking at what exactly this means. What do you need to do about it? What is a workaround, or what is the immediate action required from the user? So that's where the monitoring, health monitoring piece is very useful for those who are actually running a Ceph cluster. Then there is configuration management. So there is like like in the monitors, we store all kinds of configurations and configuration changes that are being made by the CLI or by the dashboard, or runtime changes that get made. There is a history of all configuration changes that are made to a Ceph cluster in the database that we have. So you can do things like, if you want to just roll back and say, I just want to use the defaults, I don't want to apply any of the changes that I made through all these tools, you can go ahead and do that. It's not super complicated. It's pretty simple. Then let's talk about device management. So these OSDs and other things that I just talked about, so these finally map to raw devices, and you can just map them to raw devices, or you can use something like LVM, but we kind of have the information of vendor, model, serial, so we kind of derive all that information and use them in some ways, like in Smart. So we have health metrics that we gather from these devices, and if you want to, if you opt in, you can do things like device life expectancy. So essentially, if you enable this particular module, you will be able to see if there is a particular device or a particular OSD that is about to die, so that you can take some preventive measures before that actual failure happens. So that kind of helps you avoid last minute trouble. So optionally, there is a way, like you can preemptively evacuate a failing device, like a planned removal of devices that are failing. So it kind of gives you hints as to when you need to take any sort of action based on the health status of your devices. Then I want to talk about something which is also unique, I would say, is telemetry. So we have a system by means of which there is phone, home, anonymized metrics that are sent to Ceph developers like us. So Ceph users can, and it is obviously opt-in. So if you opt in, you will be able to send useful metrics to Ceph developers in terms of which versions users are running, in terms of what the utilization is, what kind of features they are using or they are not. That gives us an idea of what our user base likes or dislikes. And also recently we've also added crash reports. So if there are crashes that are happening in the wild, we capture the version associated with that crash and also parts of the stack trace. We anonymize a lot of information that is that we do not want to capture from users or from clusters for privacy reasons. And we give users complete choice as to whether they want to opt in or not. And we take extra caution to anonymize data that should be anonymized. So even before users opt in, they have the ability to just see a preview of what they will actually be sending. And if only they are okay with it, they can go and say yes to sending that information. But the useful thing is when they do opt in, developers like us get to see all kinds of crashes or things that we need to prioritize, or a lot of times based on what the user pattern is, like a usage pattern is, or any kind of optimizations that we need to be doing, any kind of configurations that changes that we need to do. We get a lot of useful ideas from those kind of information. The next thing that we are targeting, this has not happened yet, is capturing performance-related metrics from user clusters to kind of give us an idea of how we can better automatically tune the system, or like change some of our default configuration values, etc., to work better by default, instead of users having to go change things themselves. So I think that's something we are looking forward to, but that'll also be opt-in. So if users only want to send that information, they will be able to send it. But in general, I want to emphasize the importance of such a system, because this is how we symbiotically improve the project in general. Let's now talk about some installation options. So there are multiple ways in which upstream Ceph can be installed. Currently, the most popular and the most easy is Ceph ADM. This was introduced a couple of releases ago, and a lot of users have already switched to using it. The idea is it's an orchestration interface for installation and management, and it's based on containers. And as I said, it's as simple as running one command, and you should be able to bootstrap a Ceph ADM cluster in seconds. We also have a Rook integration. So for Ceph clusters that want to run in Kubernetes world, there is a way to deploy Ceph using Rook. And then there are other methods: Ceph Ansible, DeepC, Puppet. Ceph Ansible used to be something we widely used a few years ago, but I think some users still continue to use it. But there are multiple ways to install Ceph, so that there are links to. I'm going to be sharing these slides for later consumption, so you can feel free to look at some of the documentation links that I've added here. All right, any more questions on the management side of things, or should I move to the last bit?
I guess I just had a question about the metrics. It doesn't show you which, if people use the block storage or the object storage or the file system more, is it kind of evenly distributed?
I would say it's not evenly distributed. So I would say block storage and RGW have been more widely used than CephFS. CephFS has also been used, but it's probably fresher in terms of things like erasure coding support was not there in CephFS until like a few years ago. So there have been some reasons because of which CephFS has been less used than the others. But in general, we can get an idea of what the distribution is. And I haven't really gotten and looked into what that looks like. But in general, from my interpretation, it is RGW and RBD and then CephFS.
Okay, nice.
Any more questions?
Yeah, I had a question about snapshots. I just posted it in the chat window.
So your question is regarding snapshots. If I have a snapshot at home and I am CD'd into home documents, can I access the top level snapshot within documents, or do I have to? I think you'll have to cd into the .snap daily.3 directory. That's my again. I'm not an RBD expert. That's my hunch, but I think that's what is. But yeah, an RBD expert can tell you that. I'm a Rados expert, so any Rados questions are my territory.
I think it would be a useful feature, so it'd be probably a good idea to bring up.
Yeah.
Back,
Yeah,
back,
I can. You know, that you bring a good point. I mean, any such questions, I can find the right people to answer those questions, and if they don't exist and do make sense, they can always be converted into feature requests.
yeah, just for reference, back in I think it was like 1997 or 1998. One of the jobs I was at, I was doing we put in a NetApp server for rooms, and this is exactly how it behaved. It was very convenient.
And that's it's quite possible it does behave. I haven't gotten to using RBD recently, but yeah, I can check and get back to you.
Okay, thanks.
All right, I didn't see any more questions, so maybe we can move on to the next bit. Okay, now I'm going to be talking about some of the Ceph community and the ecosystem around it. Given that we are an open source software, we have an LGPL 2.1 and LGPL 3 license for most of the code, I would say. There could be bits here and there which are not and have separate licenses, but that's the majority. All our collaboration happens on GitHub, which is all open to all. Anybody can contribute and look at the code. And all our bug tracking happens in Tracker, which is a Redmine based tracker, Redmine based. So it's tracker.ceph.com. In terms of communication, we use a lot of email lists. So we have a dev list. We also have user lists and all kinds of lists. So a lot of communication. Ceph is a very widely distributed community. It's not just in the US, it's spread all across the world. We have users in Australia. It's interesting that only last week I found out that we are going to get access to a scale cluster, and it is actually a lab that we're going to get hold of in Australia, and we'll be doing some of our upstream testing and testing some of the latest versions that we will be releasing next year. So before we do the release, it'll be mostly like a scale trial test that we run on that particular cluster. And it's going to be like 4,000 OSDs or something. And they're just offering to help us test our software on that cluster. So that's pretty cool. So that's where all these email lists and so we also have IRC. We continue to have like direct communication on IRC. There's a channel called Ceph Devel, where most of our direct communication happens. And for offline communication, email lists are the best. Beyond that, we have a lot of video chat. Again, distributed community. Video chat is the first thing that, even before before coronavirus or anything else, we were doing a lot of video chats, and we have all our meetings that we do. Some of our meetings get recorded. Some of our design discussions and quarterly presentations or monthly developer talks are all posted on YouTube. So one of the most useful resources is to go look at Ceph's YouTube channel. There's a lot of presentations, tech talks, code walkthroughs that people can actually learn from and start contributing to Ceph, or even like Ceph users can learn more about the architecture of Ceph and take it from there. But I guess the general idea is that we do a lot of video meetings, and all of our stand-ups, etc., that we do every week or every day are all on video chat. We publish releases, so we have a release cycle of a year. So every year we are doing a release. Our releases are alphabetical. Currently, we are working on our Q release. So in 2021, we did a Pacific release, which was the P release. Now we are working on Q, which is Quincy. And at a time, we support essentially 2 releases So 2 years, so anything that came out 2 years ago is what we support, and anything new comes up, then we have like 2 existing releases at any time that we support. And for all the stable releases, all these 2 stable releases that we are running all the time, we do periodic point releases. So essentially, any bug fixes or any essential features that need to be backported get released periodically, and users can consume them. In terms of distributions, we work with Debian, SUSE, Ubuntu, Red Hat. And on the right, what we have, some of the logos here are of contributors who are contributors who have like highest number of contributions to Ceph that have been made in the past few years. So as you can see, CERN is one of the biggest users of Cephfs and Ceph in general. And they were the ones who helped us do one of our largest scale testing back in like 2 years or 3 years ago. That was 10,000 USDs with the CERN cluster. And they are an active contributor too. So we have a lot of contributions coming in from CERN. So in terms of integrations, we integrate with OpenStack, Kubernetes, Rook, like I already mentioned, Linux, KVM. So these are all our partners. RBD heavily, the OpenStack community, I think at least half, or I don't know, close to half maybe, OpenStack deployments use Ceph. Kubernetes, a whole new world of Ceph and Kubernetes integration is coming up. There are already a lot of active clusters. Red Hat also has products based on that. So yeah, we have a lot of cloud-based ecosystems that consume our storage. In terms of events, so we have 2 main events. One is what we call Ceph Days. So these are one-day regional events spread all across the world. And I mean, 10 is just a number, but based on like availability of people and the interest in the community, we host multiple of these per year. I believe there's one that's currently being planned in Berlin now, that things have started to settle down. But the idea is to just get the local regional community together, and we do Ceph talks, we have user talks, dev talks, and even Ceph developers who belong to that particular region try to attend those events to have face-to-face interaction with the community. So it's usually like 50 to 200 people based on where the event is. Normally, you have a single track of technical talks and also mostly user-focused talks, because that's where we also learn a lot of, we get to learn a lot of new things from users about what their problems are, or where the bottlenecks are, or even like some useful feature requests, etc., that come in as a part of these events. So that's about Ceph Days. And the larger scale events that we have is a yearly global event, which is called Cephalocon. This is attended by much more people from all across the globe, and we do it once in a year in the spring. And I'm pretty excited to say that we finally have started planning our next Cephalocon, which is going to be in the month of April in 2022 in Portland, Oregon. So that is going to be exciting. We've had multiple. We've had once in Barcelona. We've had in Beijing in China. So those have been fun. So we're looking forward to the one in North America now. So these are like, as written down here, it's 2-day events. So we have multiple tracks. We have user talks, developer talks, even vendor talks. But these, we try to align them with releases. So every time we have a big release that we do, we try to emphasize on what's coming up in that release, what to expect from that release, and things like that in those Cephalocons. So yeah, any of you who are interested in any of these events and you happen to know one happening around you, I'd say it's worth giving it a try and attending one of these. Now I'm going to touch upon what the Ceph Foundation is. So Ceph Foundation is essentially an organization of industry members supporting the Ceph project and community. It's not just one company; it's multiple members, which include vendors, cloud companies, major users, academic and government institutions from all over the globe. Currently, we have 34 members, and the number is growing. It's part of the Linux Foundation, so it's managed by them. But all the event planning and other things are done by the Ceph Foundation. So Ceph Foundation has people from the Ceph community participating in. Ceph Foundation essentially takes care of the well-being of the project as such. So we have all our upstream CI infrastructure, our community hardware, all the documentation efforts that are made as a part of improving the documentation are funded by the Ceph Foundation. And here we have some of the existing members of the Ceph, current members, I would say, of the Ceph Foundation. So we've got some premier members here. Then we also have some general members and some associate members. So yes, Boston University is actually part of it, and even University of California, Santa Cruz, Monash University, which is from Australia, University of Michigan. These are all part of the Ceph Foundation. So that's all about the Ceph Foundation, and I think this brings me to my last slide. So this is all the information that you need to know to reach out to Ceph developers or to know more about Ceph. And as I said, the Ceph YouTube channel is a great resource for anybody who wants to learn about Ceph or wants to contribute to Ceph. So with that, I think I would like to conclude and open it up for more discussion.
All right. Thank you very much. We appreciate it.
No problem.
Thanks. That was a great talk.
Problem.
Oh,
I hope. I mean, I really hope after this talk, people know a little more about Ceph, if not everything.
Yep.
could you send us a copy of your slides so we can post on our website?
Absolutely.
Great.
Yeah, I'll put my email address in the chat window.
I think I have your email. We did talk over email about setting this thing up, right?
Yeah, that's right.
Yep.
Perfect. All right, so I can actually share my information as well. I don't think I did that. So my email is here. In case anybody has any follow-up questions or anything they want to know more, that's my Red Hat email, and that's my full name. So feel free to find me anywhere.
Yeah. Thank you very, very much. Really enjoyed the presentation.
Thank you very much for giving me this opportunity, and looking forward to talking to you guys more. This seems like an interesting bunch here.
Okay.
I particularly like the snapshot feature. I've been looking for that in file systems for for almost 20 years, and when I saw it in the NetApp like more than 20 years ago, it was basically the way I expected the snapshot to be done. And every other system I looked at when I looked at the snapshot, I was really disappointed that they didn't work that way.
Yes, I'm going to make it a point to confirm the answer to you, to your question.
I wonder if you're aware of anyone building home Ceph clusters out of Raspberry Pis.
Trust me, I've heard about it. I cannot name the person but I've heard about these kind of projects that people are taking up. I'm pretty sure there's like on Reddit or somewhere you'll find some discussions around this kind of stuff.
Yeah, it's been a to-do project of mine for quite some time, and I wanted to learn about Ceph and use it for the storage backend, for Kubernetes cluster, for my media player, for photography archive, a whole bunch of stuff. I wasn't sure if it had the power to cover all of that, though.
Yeah, I'm pretty sure. I think I may be able to share. So we have a doc writer whom the Ceph Foundation actually is funded, and he has this curious idea, and he is also interested, like any other naive Ceph user, as to let us say I have these bunch of hardware lying down my house. How can I build a Ceph cluster out of that? And he's actually writing a post about it, and I'm pretty sure he's also going to be covering stuff about things like Raspberry Pi, and like how can you create a Ceph cluster out of a Raspberry Pi. So I think you should keep an eye out on some of the Ceph posts and Ceph documentation that gets updated. The last time I spoke to him, he was kind of finalizing that draft. So there's going to be more information on what you are looking for very soon.
That sounds great. Look forward to hearing about that.
Mm-hmm.
Thank you.
Excellent. Thank you. Okay, I'm going to go stop the live feed, Jabber.
Okay.